So let me first introduce our speaker today. Our speaker is a young Janak. He's currently a PhD candidate in the Department of Computer Science at Columbia University. And he's affiliated with the Internet Real-Time Laboratory. And his research interests include Internet services and protocols, cyber physical systems, Internet of Things, distributed computing, operating systems, and mission-critical communication systems and protocols. So he was a co-founder of iptel.org. I probably logged into your website before, accidentally maybe. I was looking into some IP services. Probably I found your website a long time ago.
Oh, wow.
And he's developing software for internet real-time multimedia services. That's basically what the iptel.org was doing. I think it's still running, right? I just visited the website just a couple of days ago.
Yeah, it's running. I'm not really familiar with state it is in. It's probably being still maintained by my friends, so I hope it works, but I don't know for sure.
That's great. Well, I'll ask you to talk a bit more about it later on. So today he will give us a talk about towards self-managing Internet of Things systems. Thank you.
Thank you for the introduction. Hello, everyone. It's a real pleasure for me to be here. Today, I would like to talk to you about a problem that I have been working on for the last few years, which is management complexity in the Internet of Things. Those of you who've ever used a smart device or some kind of IoT device are probably familiar with what management complexity means. If you've ever struggled reconnecting your smart devices after you've changed your Wi-Fi password, if you needed to perform some kind of elaborate dance as you factory reset your light bulb, if you had to disable cloud backups in a newly purchased baby monitor or waited for an operating system update on your smart TV, these are all examples of management complexity that's present in modern Internet of Things or cyber physical systems, which are the official scientific terms for the systems today. Some of these issues are real and hard to avoid, but a lot of those are actually not necessarily and are kind of accidental. So let me show you what I mean by this. Here is a couple of screenshots that I have collected from Twitter showing ridiculous error messages that are being shown to people by everyday devices, right? So there's a mirror that shows that it can't connect to the network, or you get a certificate warning on a certificate expiration warning on your smart TV. This little sticker in the picture in the bottom shows that Google is down. So instead of pressing the button, please knock the door. And then my favorite example is actually a 3-minute long video which explains how one resets an ordinary light bulb, and that involves probably like 8 steps. So I feel like all these are examples of complexity that should not have been there in the first place, and we should not be exposing users of these devices to this kind of stuff. So this is only gonna get worse. At the moment, there is a large number of devices that you can purchase. Most of these are self-installable by the end user, Alexa, smart speakers, various kinds of monitors or sensors. But if you believe market projections, of which there are many online, it's only gonna get worse because the number of connected smart devices is probably going to exceed the number of all other devices connected to the internet in a couple of years. And the larger number of devices means more management complexity. There will be heterogeneous types of devices without user interface, hidden in closets, in walls. Some of these might be part of physical infrastructure. For example, you buy a new apartment or you move into a new apartment, you can easily imagine that there will be about 1,000 Internet of Things devices already installed for you. How do you interact with those? So this is gonna get even worse as the penetration of smart or Internet of Things technology actually increases. Now, management complexity in infrastructures that interact with the physical world could also mean disastrous consequences. If you have heard about the so-called Merrimack Valley gas explosions in 2018, that was a prime example of what management complexity can do. In 2018, a company operating gas infrastructure in Massachusetts was performing an upgrade of its gas infrastructure, and during the upgrade, they reconnected one branch of the system and left the other branch connected to the old systems, but which caused sensor actuator mismatch in the system, which essentially resulted in a high pressure gas being released into a low pressure system, and many fires and destroyed homes as a consequence. So as you can see, management complexity can actually mean a big problem for a lot of people if these systems control physical infrastructure. Now, these systems are also very often designed as centralized. Like, for example, it's not uncommon if you purchase a new Internet of Things device for the device to connect to a vendor-operated cloud infrastructure, and the device will typically maintain a persistent connection for management, configuration, and their data archiving purposes. If this is not done right, the operator of the cloud infrastructure can have unlimited access, as some poor owners of a device called GarageIt found out in 2017, when after leaving an unfavorable review on Amazon, the people behind the company essentially break their device remotely. So this should not have happened. And I myself actually first realized that management complexity is a big problem in a slightly different context. I essentially got first introduced to this problem when I was working on a DARPA RADICS project, which was a program run by DARPA, trying to figure out how to design a networking infrastructure for the electrical grid that could survive outages, misconfigurations, and even cyber attacks. You may think that the electrical grid and Internet of Things have nothing in common, but they are actually two instances of the same problem. A modern electrical grid infrastructure is essentially a very large scale, geographically dispersed cyber-physical systems with a lot of sensors, a lot of communication, and the grid cannot function if the devices cannot communicate. So these are all instances of the same problem. As cyber-physical or Internet of Things systems get deployed, eventually they are gonna be difficult to manage as the scale of the system or heterogeneity of its components increases. Now, this is not necessarily a new problem. People have been recognizing management complexity as a problem since probably the 90s. Some of the earliest work that I have been able to find goes back to the 90s and traces back to IBM. IBM started an initiative called Autonomic Computing, and they proposed a so-called autonomic computing architecture for managing increasingly complex computing devices. And about 20 years ago, people have begun realizing that the internet is actually getting too large and too difficult to manage. So there has been a lot of research projects into so-called autonomic networks. Essentially, research projects trying to rethink how we can manage increasingly complex internet infrastructure and computing networks. And the idea behind autonomic systems is actually not difficult to understand, and it's inspired by the autonomic nervous system, which is the system that unconsciously moderates many bodily functions in living organisms. So, for example, your heart rate, your breathing rate, and many other essential functions in your body are actually automatically regulated without your conscious effort. So the idea behind autonomic systems and autonomic networks is, could we leverage some of this and maybe redesign systems and network management to behave in a similar way, essentially to automatically adapt to changing conditions, to deal with component failures, to as automatically as possible to support system reconfiguration, environmental changes, and to make it possible for human operators to control the system via high-level intents and policies. And this can be distilled to a couple of basic principles: design the systems to be compartmentalized, decentralized, implement closed control loops where possible, and enable horizontal component interaction so that components can actually communicate with each other to determine what the optimal configuration is for the current environment, and provide a high-level interface for the human operator so that they can specify so that they can control the behavior of the system via intents and policies. We have some of this in our network systems already at the IP network layer. The IP protocol itself and many of the routing protocols like OSPF, ISIS, and even the network time protocol are good examples of autonomic protocols. They work more or less automatically. There is very little configuration that one has to do, and you typically, unless something really bad happens with your systems, you typically don't know about them. Now, if you imagine this graphically, these two pictures show the basic difference between traditional and autonomic network management. On the left, you see a network that is being managed in a traditional way using a variety of existing protocols, command line interface like SNMP, MIB, APIs. This kind of static or traditional management is where most of the Internet of Things and cyber physical systems I have had to deal with are today. On the right-hand side, you'd see a slightly different approach where there is a high-level network controller that sends high-level intents to autonomic functions running on individual computational or network nodes themselves. And then the arrows between the nodes then actually represent communication between those functions so that these systems can coordinate how to best configure the system. And all this is driven by an external knowledge base and high-level policy specified by humans. So these two pictures represent two extremes on a spectrum. Traditional system without any autonomy would require all devices to be manually managed, and on the other end of the spectrum, you have fully autonomic systems where you can specify only high-level goals, and the system or the network figures out how to configure itself automatically. This has been a very active area of research, not only in the Internet Research Task Force, but also in the Internet Engineering Task Force, which is the standard body responsible for Internet protocols. There is a working group called ANIMA, which tries to rethink which tries to design an interoperable model for these autonomic functions and autonomic protocols. Lots of interesting work is going on in there. And you would find decades of research, decades of academic research on autonomic network and system architectures. So there is plenty of work, and and a lot of papers to look at, and a lot of interesting protocols and ideas. So I have been wondering if any of this could be applied to Internet of Things systems or cyber physical systems. Clearly, Internet of Things systems are at the intersection of computing and network systems. So we would have to apply autonomic principles both to network nodes, Internet of Things sensors and actuators and computational nodes, and also at the network itself, at the various network technologies, routers, application servers, network services that connect all these. And we have been working on a couple of research projects, trying to enable using these autonomic principles in some of the systems that we have been working with. So I'm now going to introduce you to three research projects that I have been involved in since about 2017. The first is an emergency network architecture for the electrical grid, which represents a very large-scale geographically distributed cyber-physical system. The second project will be a network service for sender data storage that we have been developing for around campus. And the third project will be a reimagination of how Wi-Fi capable Internet of Things devices could join and remain connected to enterprise Wi-Fi networks. So these are all these three efforts are actually an attempt to apply autonomic principles to network services and protocols to design more resilient, robust systems. But each of these applies those principles at a different scale. So let me start with the electrical grid, because this is the first project that I actually, where I actually started thinking about management complexity. So we worked as part of the DARPA RADICS team, and our goal was to design an emergency network architecture for reconnecting the US electrical grid in case of a blackout or a cybersecurity incident. DARPA is worried that at this point, because the electrical grid is so complex and so heterogeneous, they are worried that at this point, malicious activities are not stoppable, and sooner or later somebody will be able to breach all the infrastructure that's running in substations and generator rooms and to bring the electrical grid down. So they have been wondering, they have been trying to come up with a contingency plan, and essentially thought, well, if we can't prevent the networking infrastructure that's powering the grid from being affected, maybe we should start designing a backup network infrastructure that could be deployed in the aftermath of this kind of event. And this is something that I have been working on, and we worked as part of the larger institutional team, and we designed a self-configuring, self-managing network architecture that you see in the picture in the upper right corner. And that architecture was brought to Plum Island in New York, which is a tiny little island highlighted in the red circle off the coast of Long Island. And this is a military-run island, and what DARPA essentially did is that they created a small-scale model of the East Coast electrical grid on the island. They brought in the exact model of all the infrastructure that's powering the Eastern Interconnect from Washington, D.C. to Boston. And they essentially simulated a series of incidents, blackouts, and reconfiguration. And in each of these incidents, they would measure how much time it took for the backup network architecture and services to recover. Now, just to let you know what the US electrical grid looks like, this complex looking picture actually shows the networking model of the US electrical grid. So as you can see, there are many building blocks, communication flows, and many protocols. The takeaway message from this diagram is that the communication subsystem in the grid is actually pretty complex, and it includes a mixture of real-time and non-real-time communication flows. There is voice over IP traffic that is crucial for the grid to function. There are senders, SCADA systems, and there are phaser data concentrator units that generate a huge volume of data. So you can imagine the networking infrastructure that is powering the grid as a very large cyber physical system. Now, what most people don't realize is that the grid cannot function if the network goes down, and the grid cannot be restarted if the network app is not operational. which presents an interesting chicken or the egg problem, because if the network is down, the grid cannot be restarted, and if the grid is down, the network will not be functioning because there will be no electricity. So, we've designed an emergency self-configuring network architecture called PhoenixSEN, whose diagram you can see on the picture on the bottom. And the idea is pretty simple. We've designed backup infrastructure, put it in waterproof Pelican boxes, and that network infrastructure includes switches, computers, voice over IP devices, and if something bad happens to the primary network infrastructure in the electrical grid, U.S. National Guard or the Army would actually deliver those boxes to substations, utilities, and generators, and the operators at these at those points would essentially reconnect their grid infrastructure to this temporary network. And a pretty important design decision required by DARPA was that this backup networking infrastructure must be as self-configuring and as easy to manage as possible, because it will be operated by grid personnel, not necessarily by networking people. So we have spent a good number of years trying to figure out how to design a mesh network, how to make this configurable, how to make this self-configurable, how to use a variety of link layer technologies, including utility fiber, wireless links, and many other things. And because this network architecture has to be functional in the absence of the internet, it also includes a whole bunch of built-in services and protocols so that the grid could be restricted only using this network architecture. Now here you see the actual physical prototype that we have built and tested on Plum Island. This shows a small subset of the prototype. The picture on the left shows these Pelican boxes. Each box has switches, routers, a battery, interfaces to various kinds of links, and in total, our prototype consisted of about 35 of these, which would have been sufficient for restoring the electrical grid on the entire three-state area. And then on the pictures on the left, you'd see the internals of the box. As you can tell from the pictures, hopefully, this is our ordinary hardware. There is no special hardware, so we have built this using ordinary off-the-shelf components, and essentially made the system self-configuring using custom software. And this slide shows the internal software architecture of each node. All the nodes in the PhoenixSEN architecture are identical, and there is a minimum amount of configuration that the substation personnel or generator operators have to do to actually connect the node. Everything, all the configuration from all the services that are including voice over IP, NTP, DNS, DHCP addressing, all that is either generated from a model or automatically configured or configured remotely by DARPA from a control center. Now, we have evaluated this network architecture repeatedly from 2016 to about 2020. Unfortunately, the last evaluation exercises got interrupted by COVID, but the largest exercise that we have performed include about 300 devices, 70 voice over IP phones, and 32 SCADA systems, including real-time devices. So in each of these exercises, DARPA would essentially randomly disrupt, reconfigure, or disconnect various parts of the system, and then they would measure how long it takes for the network and for the services to reconvene, and they would essentially evaluate whether or not the toolbox or the infrastructure is good enough for speedy recovery. And then the goal of this research project was essentially to produce a networking toolbox for utilities or generators or electrical grid networking operators to incorporate into their portfolio of networking technologies. So this is where I first got exposed to the management complexity problem, because as you can imagine, the infrastructure and the electrical grid is actually very diverse, and you'd find all kinds of problems with statically configured IP addresses, static configuration in SCADA systems, in senders, in router switches. So it's actually very difficult to reconnect the electrical grid if parts of the infrastructure are not online or are being under an active attack. So I first began to realize that there might be a management complexity problem in this kind of system. The second the second project that I worked on is a project that we internally called SenSQL, which is a geographical discovery service for sender data. Now, one of the services when we were working on the PhoenixSEN infrastructure that we didn't have was a distributed database that we could use to store sender data on each substation. Like, we were not able to design a distributed database that could function in that system without having a single point of failure, which kind of limited us in what kind of forensic activities we could produce, because the forensic activity trying to figure out why parts of the grid are not operating actually requires a lot of senders in the network, and those can produce a lot of data. So I've been working on trying to design discovery service for databases that could store large volumes of data generated by Internet of Things senders. And as you can imagine, in most, this would have been useful in the PhoenixSEN system, but it's useful in practically any IoT system that you can imagine, because in all systems that I have seen, sooner or later one has to have a database, and one has to store the measurements produced by IoT sensors in that database. Now, you might be wondering, like, what people do today. In most cases, people today restore to vendor databases running in the cloud. So if you purchase a modern IoT device, or if you try to set up your own home smart infrastructure, you would typically have one database running somewhere in the cloud provided for you by the vendor of that device. Or if you're brave or technical, you might be setting up something like a home assistant on your Raspberry Pi or Intel NUC, which will give you one database where you can store all the data. But so that works for small or non-critical deployments. But as soon as one starts to scaling that infrastructure beyond a single entity controlling all the infrastructure, this is an issue. So I've been wondering about whether or not we could design a database discovery service that would allow us to build one federated database out of many smaller databases, where a subset of senders would be storing data in a database near the sender. And to give you an example, this is actually something that we have been building for our campus. The picture on the right show a view, an OpenStreetMap view of a portion of our campus, and you'd see these little green dots. And this is a mixture of both physical and virtual emulated IoT devices. We actually have about 10 real physical devices, and the remaining green dots are virtual emulated IoT sensors that we have been emulating on on the local network, and this represents some future large-scale big deployment of IoT sensors across our campus. And I would like, because Columbia is a huge institution that consists of many departments or many internal, many buildings and many individual parts, it's unlikely that as these sensors get deployed across campus, that they will be operated by a single entity. So we have been wondering if it might be possible to build a system where different departments or different buildings or even facilities, public safety, different organizational units within Columbia could operate their own smaller collections of IoT sensors and yet contribute those sensors to a wider university-wide system. And ideally, we would like to be able to execute SQL-like queries across this entire infrastructure. So, for example, if you look at the example on the left, that's a very simple SQL spatial query, which returns the measurement from all carbon dioxide sensors inside David auditorium, which is the little oddly shaped room in the smaller pictures in the bottom right corner on Columbia Campus. So we imagine that that the IoT infrastructure scattered around our campus is run by multiple organizational units, and we would like to try to build a system that can query that infrastructure without the user having to specify which database to connect to and how to get the data. And the type of the queries that we would like to support include basic SQL spatial types of queries. So, for example, find the maximum particulate matter value in Manhattan or near a specific longitude latitude. Calculate the daily average temperature in our kilowatts and so on. So these are all pretty simple SQL spatial queries that are not difficult to execute once we can locate the various databases that store the data. Now, before I describe how we are building the system, I'd like to make a slight detour and talk a little bit about a framework that inspired this work, which is called Allocation to Service Translation Protocol. Allocation to Service Translation Protocol is a protocol and a service that is being used in voice over IP communication systems when you dial 911. Imagine that you dial 911 from your mobile phone, and your call is gonna be directed to a so-called public safety answering point near you, which is essentially a call center that is hopefully not far away from where you're located. And so for this to happen, your smartphone must be able to determine its longitude and latitude, which it can do from the network or from GPS. And then it uses a lost service to translate that information to the nearest public safety answering point. So your phone would submit its longitude and latitude to the service, and the service would traverse a hierarchical sequence, structure of servers, trying to determine which public safety access point covers the geographic area near you. So this is an idea. That inspired my work on the SenSQL project. So I was wondering if this exists for voice over IP calls. Maybe we can design a similar service that will take a polygon, so-called region of interest, and translate that to the database or a set of databases that serve that region of interest. So this slide illustrates the basic SenSQL approach. So imagine that there is an IoT application like a dashboard or some sort of IoT integration application which submits SQL query to a SQL proxy. The SQL proxy, that SQL query will include location information such as room, geographic area, longitude, latitude, building, floor, or that kind of information, and this SQL query will be submitted to a SQL proxy, which extracts the spatial information and uses a loss-like service to find the databases that serve that area, and that loss-like service will map a service region, which is a manually or automatically determined geographic region for each database to the SQL query. Now, then the SQL proxy will translate the SQL query, forward it to the relevant database systems, and if it gets any data, it will aggregate the data on the way back before submitting it to the IoT application. So this is the basic idea. There is a bunch of SQL databases distributed across our campus. For each database, we have defined a service region, and then we've built a discovery service that could automatically determine which database is related to the SQL query submitted by the application. Now, this is what the architecture of our current system looks like. In the upper left corner, you see the actual application, which in our case is Grafana, a web-based dashboard that we use to plot nice looking graphs for our IoT centers. The Grafana dashboard submits a SQL query to the SQL proxy, which is implemented using an open source SQL proxy called Presto, created by Facebook. Presto will consult a local SQL database, which contains a local copy of spatial objects that we have downloaded from OpenStreetMap. This includes a subset of the OpenStreetMap data for our campus, including buildings, floors where available, roads, parks, and so on. And we also combine that with some private information from within our buildings, which is the floor plans for individual floors and rooms in our office building. And then these three polygons and in the bottom show the individual subsystem that make up our campus IoT infrastructure. So you can imagine that the blue subsystem could represent the computer science department, the red subsystem could represent electrical engineering department, and the green one could be public safety. So each of these are independent. I call these autonomic cyber physical systems. Then there is a bunch of IoT centers in each and a database. And then the discovery service then binds all this together, making it possible for the Grafana dashboard to essentially query, to issue a SQL queries that span all three systems. Now, each autonomic cyber physical system looks internally like this. There is a database and a so-called geo-publisher service and a storage agent, MQTT, and a whole bunch of support building blocks and infrastructure. But the idea is actually pretty simple. We do have a collection of Internet of Things center, which in the current incarnation are LoRa centers that periodically produce measurements, and those measurements get saved into a Postgres database running on a Raspberry Pi. And then that Raspberry Pi runs a publisher service, which announces the availability of the database to the discovery service, and that way this small isolated island of functionality becomes available within the larger campus-wide ecosystem. The tricky part in the design of the system is the actual discovery service, which is fairly difficult to design if you want to take advanced requirements into consideration. For example, for the system to be practical, it must support large and complicated regions of interest, meaning polygons containing many hundreds of points. It should respect jurisdictions in case you want to query systems that span jurisdictional boundaries, and it should also be possible for the computationally expensive operations to be performed by the client, by the application that is actually using the resolver service. And here is the prototype service of the discovery service that we have built so far. This is directly inspired by the Lost Reservoir architecture. So each geo publisher running on the database that makes itself available within the campus system publishes a service descriptor to a so-called ACPS registrar, which then submits the service record or service descriptor for the database into a database that is currently implemented using DNS service records. And then we have built a resolver service that is running on in the cloud, very close to the application that is capable of traversing those service records, locating the corresponding databases, and that information is then submitted to the Presto SQL proxy. This is far from ideal. This architecture sort of works for our campus, but it's still not really scalable enough to scale this beyond our campus. For example, we would like to be able to demonstrate that this can work across Manhattan, so that one can query IoT sensor infrastructure installed in different neighborhoods, but we are not quite there yet. Okay, and the final project, and this is work in progress that I have been working on so far, is rethinking how Wi-Fi connected Internet of Things devices could actually join and remain connected to Wi-Fi networks. So if you've ever purchased an Internet of Things device, you probably know what it takes to connect it to Wi-Fi. For example, in case of the Amazon Alexa or Google Home, you have to download the corresponding application. You have to enter your Wi-Fi name and Wi-Fi password into the application. Typically, the IoT device will create a temporary Wi-Fi network. Your mobile phone will connect to that Wi-Fi network, losing internet connectivity in the process. And then it submits your Wi-Fi password into the Wi-Fi access point and so on. So this is a kind of painful and complicated process that doesn't really work very well. In our lab, we have about 20 different IoT devices from different manufacturers, and it's actually pretty difficult and confusing to connect them all to the same network because each vendor and each manufacturer has a different terminology, a different application. So you have to maintain a variety of applications on your smartphone and so on. So I feel that even the very first step of setting up IoT infrastructure, connecting the devices to the Wi-Fi network, is actually an unsolved problem. And this is further complicated by the fact that many of these devices have no user interface. And in the future, many of them will actually be installed in places where they cannot be physically reached, like for example, a smoke detector installed on your ceiling, or other devices that are part of your fixed apartment infrastructure and are installed in an inaccessible closet. Plus, there are more advanced scenarios, like here in New York, many buildings are apartment buildings with tenants coming and going. So how do we deal with reconnecting smart infrastructure that is installed in those apartments to to the devices of the new tenant, and then making sure that the tenant has no longer access once they have left. So there are many corner cases and interesting application scenarios that current technology cannot really solve. So we have been working on this for a bit, and we're trying to figure out how to make this possible, ideally, how to minimize the involvement of the user in this entire onboarding process. And that might be to some extent possible if, for example, the manufacturer of the device gets involved. For example, if we could distribute cryptographically signed certificates to the user when they purchase a new device. We have been wondering about how to do this on a scale. Like imagine that you're moving into a new house, and the new house has smart lighting, smart light bulbs. You typically will have at least 10 of those. How would you connect all of them to your Wi-Fi at the same time? And then we are also wondering how to design this in an interoperable way so that you wouldn't have to have an individual. You would not have to have a vendor-specific application for each device. And we've been trying to build a protocol and network services to run on the access point and on the device. Here is a very preliminary approach that actually involves the manufacturer. So we are trying to design a certificate authority that manufacturers could run, where they could transmit cryptographically signed information to whoever's purchasing the device through the chain of resellers, and you're designing a commissioner application that might be vendor neutral and independent, so you could only have one running on your smartphone. Plus, you're trying to develop a network agent running on OpenWRT that will use WPA enterprise authentication to actually simplify the authentication and authorization process. And so far, the prototype looks like this. We have been running this in our lab. We have a daemon running on an OpenWRT router and a very simple agent running on embedded devices with no user interface, running on ESP32 platforms, and then a simple smartphone application that actually can connect the devices without the user having to do anything. So there is a couple of scenarios that could happen in here. If the user purchases a new device and they are capable of retrieving a certificate for the device from the manufacturer, the very moment that they unbox the device and connect it to power, the device will automatically discover the smartphone application if it's running, and then it gets automatically connected to the user's Wi-Fi network without the user having to do anything. And this works for one device, but also for multiple devices. And if that's not possible, if, for example, there is no certificate from the vendor, then the application will gracefully degrade, eventually asking the user to enter the Wi-Fi password and device ID and other information manually. So in the ideal case, this is a zero-touch Wi-Fi onboarding system, kind of similar to Wi-Fi Easy Connect, which gracefully degrades if the infrastructure isn't there, or if the manufacturer of the device isn't cooperative and doesn't provide digital cryptographic signed certificates and other information. And then we are trying to think through some of the corner cases and more advanced scenarios, like remote enrollment, where you're trying to onboard devices for your parents, but you cannot be physically present, automate enrollment of large number of devices, or support more advanced scenarios like Airbnbs, rental apartments, offices, and hotels. So this work is very much work in progress. All right, so to summarize my talk, since I'm kind of running out of time. So I've been working on a whole variety of Internet of Things and cyber physical systems, and I have seen that all the systems that I have been involved in are actually largely statically configured and centralized. There is a decade of research on autonomic systems, and I'm kind of wondering if any of that might be applicable to the Internet of Things, and whether or not we can use some of the ideas developed in autonomic systems to make IoT systems more resilient and self-managing. We kind of already have that at the network layer, because many of the IP layer protocols are self-managing and autonomic already, but we lack this kind of functionality at the application layer. And I've been trying to design a couple of network services and protocols to test out these ideas. I have built a PhoenixSEN, which is a network for large-scale cyber physical systems, specifically geographic, SenSQL discovery service for federated distributed storage of sender data, and I'm currently working on trying to rethink of how Wi-Fi connected IoT devices can get connected to Wi-Fi. And with that, I'm finished and happy to take any questions you might have.
Sure. Thanks a lot, Jan. That's very, very informative.
Thank you.
Before I start asking you a lot of questions, I'll just let our audience to see if you guys have any questions.